Cool. It's a booming voice. Okay, we're going to get started here. Thanks for coming. Welcome. So this session of RCON is primarily about the K framework, why we need it, what we're using it for, what we're building, and you'll get to see a little bit of the K framework as is. Okay, so then we'll talk a little bit about type theory at the end. Please don't hesitate to ask questions while we're going through if you have them. Okay, first of all, so we're developing the K framework for Rolang, and I know that most of you have probably seen and played with Rolang already, but just in case some of you have not, let's just talk about Rolang for 30 seconds. Come on. Oh, this is really disappointing. Aha. Okay, so Rolang is a language designed for smart contracts on the RCON blockchain, and it's somewhat unique in the sense that its main computational step is sending and receiving messages. And so Rolang is sort of ideal for network setting, and computations are performed by a bunch of processes running in parallel, and each of them are sending and receiving messages. So just really briefly, just in case you're unaware of the syntax of Rolang, we're going to be using this in just a little bit, so I thought I would at least talk about it. This is part of the Rolang tutorial that you can find online if you just Google Rolang tutorial. This is the first example. So this new construct just gives you a new unforgeable name, which means you have a private channel on which you can send and receive messages within the scope of this contract, within the scope of this body. Then we define a contract that listens on this new channel, hello world, and whatever it receives, it saves as return, and it binds to this variable here. Contracts will always receive a channel. And so it receives the channel and it sends the text hello world over it. This runs in parallel with another spawning of a new channel called my channel, which is this unforgeable private channel. And then we break security by sending my channel over hello world, so this contract can see what this new my channel was. And what we end up doing is we send over this private channel, we send the text hello world. So if you did not really quite catch that, the main things that we're interested in here are this right here, this construct where we say this is a channel, this is the send, and this is what we're sending. And then there are contracts that listen on channels, and then there are other things, and we're actually going to be looking at those in just a little bit. Okay, so let's go back to this. Okay, now what is the K framework? K framework is a framework in which one can define formal semantics of a language. Why in the world would we want to do this? Well, first of all, it's very useful in formal verification, and that's the main reason, the main way in which we'll be using this. The second, I'll get to the second reason we want to in just 10 seconds. K framework uses a logic to reason about languages, which is matching logic. And so you'll define all your syntax, and then you'll give a rule. You say, this bit of syntax rewrites to this new term, which rewrites to this other new term, which rewrites, and then you specify a bunch of rewrite rules, and then eventually you define your whole language by how things are supposed to rewrite. So you may be thinking, oh, well, that's like really not very hard to define a language in K framework because this matching logic is so nice. In one sense, when I first started looking at it, I was like, oh, what a beautiful natural way to do it. And it is beautiful, and it is a natural way to reason about languages, but certain languages can get very messy as you try to do this, but lots of fun still. So So the main takeaway of this slide is that K-framework is really fun to work with. Okay, so why should we care about these semantics? So K-framework was developed by Grigore Rochu and his team at the University of Illinois. And he has this little introductory video, to convince you to use K-framework. And this is the example he gives. And so this is a program in C. According to the official C semantics, which is this huge, confusing, messy document that no one wants to read, this should be undefined. But depending on the compiler, he gives two examples of two interpreters that will return either 3 or 4. And so one of them does 3, one of them does 4. So there is some sort of misbehavior in your languages if you don't have the semantics. Or there can be, at least. And it can sort of depend on the compiler interpreter you're using, what you get. Most functionality will probably be the same, but if you really want to reason about your language and reason about programs, and do formal verification in a really high-stakes setting like a blockchain where millions of dollars are on the line or euros are on the line, then you want to be very precise in what you're reasoning about. So the point of defining semantics is one, that you have sort of a baseline definition of your language so that anyone who's trying to use the language knows exactly how it should work, and there's sort of the definition. 2, so we can do formal verification like we talked about yesterday in our panel. The main advancement of K-framework, aside from providing all these really nice tools, which is actually probably the main advancement, so let me reword that. One advancement of K-framework is that K-framework allows you to define semantics in what Grigore Rochu calls like this really fun, interactive way. It even incorporates colors, which we'll see in just a little bit. Okay, so let's see what in the world, what a language looks like defined in K. So this is a language, very, very simple language, and it's just a language you can sort of add 2 integers, and that's all the language is good for. So our language is called EG because this is an example. And a language is defined using modules. There's this main module, which itself can be split up into smaller modules, and then there's this syntax module where your syntax goes. And what you do is you say, okay, in my syntax model, I say, okay, here's a bit of syntax. I say fun, not for fun, but because that looks like function, it stands for function, and here's my function. It's add, takes one integer, and takes a second integer, and then it adds them. Well, it doesn't add them until I add this rule. And I say, here's the rule. I say add 1 int, 2 int, rewrites to the first int plus the second int. And K has this sort of plus functionality built into it. Okay, so let's actually look at this and sort of interact with it a little bit.
Can you talk a little bit about why you need to separate syntax from semantics?
So a priori, you don't actually need to necessarily, like K will actually let you have it all in one module, but there is an important difference. And this is a good point. Thank you for bringing this up. So the difference between syntax and semantics is important in the sense that syntax tells you what you're allowed to write in your language, what a correct sentence, what a correct program, what form it can take. Semantics tells you what it means. And so, in particular, yeah.
This isn't specifying semantics. This is specifying a rewrite rule here. You can take a model of this in sets where int maps to the set of integers and plus int maps to the function on integers. And that is the semantics of this syntax. Right here, it's just defining an abstract rewrite rule that says, if I see add
Thank you. So in particular, in this language, I can't, write a string. I also can't just write a list of integers. I can really only write add one int and another int. That's the only thing that's allowed in my language. So I will admit that I lied to you a little bit. That's not quite the full definition. There's a couple other things that you need when you're compiling in K, but that was like the essence of the definition. So, we have things like, other things we need to import. Okay, so this is the true, actual definition, and I'm no longer lying to you. Okay, here we have our syntax, which is our function that's an add, and then we're defining a syntactic category program, and our program, we're now going to allow integers or functions in our program. Yes?
So again, this is a parser, right? Int just says a string of digits where digit is the character 0 through the character 9, and it's just parsing this out. It's totally syntactic.
Sure.
The semantics come when you run it, and the K framework assigns those semantics at runtime to be sets and functions.
Okay. Yeah, and that is sorry?
Why is it strict?
Okay. Yes, I'll come to that in just a bit. I want to talk, so strict means that it will evaluate its arguments before it rewrites this function. So we have this rule from before, we have this category, so we've just added this syntactic category. Anytime you make something strict, you have to tell K what, you have to define something called the K result. And that's pretty much, that has to do with heating and cooling rules, and so K just needs to know when it's done sort of evaluating the argument inside. And so you say, once you've gotten an integer, you're done evaluating these arguments, and you can rewrite the function. It's pretty much what this is saying. And then down here is a configuration. And this is a very important part of the K framework in that when you reason about the behavior of a language, you have to reason, you use these cells. So the entire program is always wrapped in a T cell, and then the computation happens in a K cell, and then you can have all kinds of other cells that might keep track of other information. Sure, yeah.
Is it possible to write like nested rewriting rules, like other day will be rewriting to another function?
Absolutely. In fact, often that is necessary. When the behavior of your function is a little more complicated, you need to break it up into steps and just sort of have this sequence of rewrite rules. In case you didn't hear, the question was, is it possible to write nested rewrite rules in the sense that, one function rewrites to some term, which then rewrites to a different term, which, et cetera, until you've reached the output of the function. And yes, that is important. Okay. Yeah, so any, if you need to keep track of a map or a stack or, all kinds of things can go in other cells. Okay, so let's actually just take a look at this. We're going to run. Okay, so right now I'm in the folder containing this K file corresponding to our example. First of all, let's compile. So in K, use this function compile. So compile eg.k, and then you have to choose what backend you're using. You can use Java or you can use Coq. And I believe Haskell as a backend is on its way. So we compile, and now K is happy, and now we can run tests. Okay, so let's look at this test real quick. Just a simple, we're just adding 7 and 5. So, great. So we'll say krun test.eg. So what krun does is it will get that test you've written, it will stick it into that main K cell, and then it will apply all its rules. Once it can't apply any more rules, it gives you what it's come up with. So, the slowest adder of all time. Okay, so we have our T cell, we have our K cell, and inside is 12, as we wanted. Okay. So in this case, the cells really don't play an important role. In general, you want your computation happens in a K cell, and then any information you need to keep track of as you're computing, like a counter or memory or a map or something like that, you stick in other cells. And then as you're writing rewrite rules, you can sort of reference those cells, and you can say, okay, pull this information from this cell as we do this. Yeah.
Is this cell, it features that the cell represent some component of the memory model of this language? Something like this, or you have to stack the network applications and
Yeah, so you'll definitely sort of embed your memory, any memory you need to keep track of in cells that are along with this K cell. I'm trying to think of.
But that's just for displaying it for us, right? The K framework could do all the computation, all the verification without even a single cell, right?
Well, I'm not sure quite how to answer. So the question was, the cells are just for sort of visual purposes, and they're not actually necessary for K. In one sense, they are. I think the way that K displays the cells is useful explicitly for visual purposes. Although in another, you still need to. You still need to define your entire language based on just rewrite rules. And so when you keep track of your memory, suppose you have some element in a map, and you're sort of key value pairs or something, and you look up the value for a certain key, and then you say, okay, once I've grabbed this value, I need to delete that key. Your rewrite rule will be you can write a rule that looks it up, that grabs it and that deletes it. But you do need to sort of at least have some place where you have your memory that you can write a rewrite rule for. So it's very natural, both for looking at it and also just for reasoning with these rewrite rules. Does that answer the question? I'm not sure if I can give a conclusive, it is totally necessary or it's not, but those are my thoughts, at least. Great. Okay. So let's look back at this language real quick. And I wanted to sort of show the nuances of, at least some nuances of writing something in K. So actually, before we look back at this, let's look at our test, and let's do something a little more complicated. We're going to do associative adding, and so we're just sort of going to compose this function. So we're going to say add 7 to the sum of 2 and 3. Okay, so just looking at it, based on the function, and we want the functions to be able to compose with themselves most of the time, and so. Well, I guess not necessarily most of the time. In this case, we most certainly do. And so looking at it, we say, okay, this is just 7 plus 2 plus 3, which is, again, 12. Okay, so we run into a slight problem when we try to run it. Where am I? So let's run this again. Okay, so we've run into a slight problem, and it's complaining, and it says unexpected token add. And what it's referring to is that when we stuck this add inside of the add function, we had originally told k to look for 2 integers, and this itself is not an integer, it's a function. And so, when we look at it, we say, oh, well, if you evaluate this, this will give you an integer. K is not quite smart enough to know that, and so you need to sort of, you need to say, okay, well, in this add function, yes, I want to be adding integers, but I can also put in, I also want to be able to compose. And so not only do I need integers to be part of this function, but I also need the function itself to be able to put inside. So instead of using int and int there, we're going to replace this with program and program. Okay, so putting a category for the entire program is usually quite broad, but in our case, it only encompasses ints and functions, and our only function is this add. So this is exactly what we want. No. So the question was, do we need to update the k result? No, because what we want this add to evaluate its arguments before it rewrites, and the only rewrite rule that it has is when it accepts integers. So we want, before this gets evaluated, it needs to return integers. And so the k result essentially says once the product, like the result of evaluating should be an integer. And that way, we know that it will evaluate, it will give us an integer, and then we'll be able to apply our one rewrite rule.
And if we had a set of rewrite rules that would cause us to end up in a different category than the integer, then k would yell at us that our program is kind of terminated, right?
Well, instead of yelling at you, it will just sort of give you this messy result, and we'll say, here's what I came up with, and I can't rewrite anymore, and so, look. And
There are cases when your programs don't terminate under your semantics.
Well, yeah, in one sense, yes. So there are ways to define semantics. You can define an infinite loop that it will just never stop being able to rewrite a rule. So that's one thing, but also, yeah, when you say, there are ways to have semantics that doesn't terminate the program, in one sense, yes, because it will give you sort of, you may have an idea of what you want the program to have done, and it won't. So I can just do a really fast example of this, actually. We're good? Okay. But yes. Okay, so now let's rerun this. Sorry, I need to compile again. Got nervous for this a second. So compile eg.k, backend Java. Now we can run. Oh, that's the problem. Crap, no, that's not the problem. Wait, say that again.
Yeah, because your definition of add has...
Thank you. Haha. Okay, thank you. Great, okay. All right, now let's talk about something slightly more interesting. Let's talk about let's look at some examples of rules that we might get from the K framework as it stands. So the K framework of Rolang is not actually finished. It's a work in progress, very much a work in progress. And so, anyway, as it stands, let's look at some rules that we might see. Okay, so here's an example of rule. So in Rolang, we have multiple concurrent threads. Because processes run concurrently, we need to be able to simulate a bunch of things running all at the same time. So every process has its own thread. And every thread will have a bunch of cells that keep track of all sorts of information. And what we're saying here is we're saying, okay, so I should say one really wonderful thing about the K framework is these ampersands, or sorry, ellipses. Ampersands are different. Ellipses. That they just sort of tell you, like, what this is saying is you want to find a thread that somewhere in the thread there's a K cell. You don't have to specify where in the thread. The thread can contain all sorts of other information, but you say somewhere in the thread there is a K cell, and somewhere in the K cell you don't really quite care where. You have one process par another process. So these processes are supposed to run concurrently. And so what we do is we say, okay, we're going to take these concurrent processes and we're going to just take the first one. And so we're only going to keep the first one in this thread. So we rewrite to P1 here. And then we spawn a new thread here. And we say, spawn a new thread. And the new thread will have sort of some structure that it comes with. But we say, in the K cell of this new thread, stick P2, the second process. And so that way it will have separated the threads. And now we have two threads running in parallel. This tag right here at the end is so that we can explore any behavior that is possible of these rewrite rules that we've defined. So essentially what that means is that in any given situation, you may have multiple rewrite rules that can be applied, or maybe one rule that can apply to different terms in different orders. And so you can ask K to show you the result of applying this, either applying rules in different orders or applying, this one rule to the processes in different order. And so sometimes that won't make a difference. Sometimes it totally does. In particular for Rolang, there is all sorts of non-deterministic behavior that's possible. And so this functionality of K is like a really fun and beautiful thing to work with. I should mention that you would probably be surprised at the amount of non-deterministic behavior that can arise from a program. There are a bunch of tutorials on K framework that Roshu has published in his team, and he sort of gives some examples of where non-determinism gives you really surprising results. Because essentially you're defining a logical system where you have syntax that's allowed, and you also define these rewrite rules, and it is not always straightforward to, in fact, often it's very complicated to know exactly what are all the possible results given these rewrite rules you've defined. And so this is a very useful piece of functionality that K has. Okay, so we're actually going to look at a snippet of code in Rolang that this could potentially form part of a contract, although I'm not sure why you would implicitly include a race condition. I mean, like, you just never know how this is going to turn out. Sorry? There we go. Yeah, that's a great. Okay, now I know. So leader election would be a great situation in which a race condition is desirable. Great. So this is a snippet of Rolang code. For those unfamiliar with Rolang code or this syntax, what this is, this for expression is a listen on the channel at nil. So channels always have the form at and then some process. So nil is the empty process. So we're listening on this very generic channel at nil. And we're listening for something of the form at x. And whatever comes, we will bind to x and then substitute in this expression here and then run that expression. We execute. Okay, so on @nil, we send both the processes 1 and 2. I should mention an interesting and very actually nice nuance of Rolang is that you always send processes and you always receive names. And so that's initially a little bit confusing. But essentially what's happening here is that we send over @nil, we send 1. Anything that's listening on 1 will not receive the process 1, but will receive the name @1. Sorry? Right, listening on nil. And that is just a really, again, it might seem a little bit counterintuitive, but it's a really nice, it just sort of really simplifies things. So it's quite nice, actually. Okay, so one of two things can happen. Either this for first hears 1 on @nil, or it first hears 2. And the way we're going to find out which one it heard is that whatever it heard, it's going to send on success channel. It's going to say, 1 succeeded or 2 succeeded. So let's just run it and see. So we're going to run this using the K framework as is. Okay. Great. So just so you can see, our test is written here, just so it was there. We're going to say, great, krun test.test.row. Okay, so it's a little bit. Okay, so let me make this big. Is the text big enough to read? It looks probably big enough. Okay. Great. Okay, so as you can see, there are a bunch of cells. It keeps track of different things like, where are the sends, where are the receives, et cetera, et cetera. And right here, there are 2 threads that have resulted from this. One of them, we're sending 2 over nil. The other one, we're sending 1 over success. So what happened in this race condition was that 1 got to listen first, and 1 sort of beat 2. But of course, there's another result, and when K is executing, there are all these possible results that it could give you, and if it does encounter sort of multiple options, it just sort of chooses one, and it goes on that. So if we were to execute K again, so if you were to execute this multiple times in a Rolang, you might get different things every time. But in the case of K, it sort of chooses one and sticks to it. So you have to coax out of it, extra behavior, and you have to actually explicitly ask for it. Okay. So the way we do this is the following. We want to compile our K file, but we want to tell it. So we say transition is, and this is where we put that tag. So if you remember from a few slides ago, there was a tag that says parallel processes on that rule I showed you. And so we're actually going to do the tag send, receive, match is the tag that's on there. So what this does is it will compile, and then anytime, now it knows that anytime it applies the rules that correspond to this tag I've given it, then it will put a little marker there, and then if you ask for it, it can show you, at this marker, I could have chosen all these different things. I chose this one, but I could have chosen, et cetera, and then it will give you all the resulting cases. So a priori, when we look at this, we should say, okay, well, either 1 gets to listen first or 2 gets to listen first, and so there should be 2 possible scenarios, right? So let's see if our intuition holds. So we're going to run the test, and we're just going to tell it to keep an eye out. So this tag search keeps an eye out for those transitions. So looking. Great. Cool. So again, we have the case that 1 beat, but you'll notice that this says solution 2 at the top. And so there is, the first solution says, 2 beat 1, and the second solution says, 1 beat 2. And so K lets you explore. Cool. So, okay, this is pretty much the end of the explicit material that I have on Rolang. I just want to say, before transitioning into sort of type theory things, that there are more tools that come along with this. This is not the extent of the glory of K. K also gives you, proof functionalities, and while they are a bit tedious to work with at times, there are wonderful groups like those at DABHub who have developed very nice tools and who are making those tools available in such a way that formal verification and proving things in Rolang is, well, Rolang is going to be hard, but in certain languages is more natural. Okay, let's move on to the type theory. While I remove my things and Mike sets up his things, are there any questions? Yes?
So you are working now at the definition of Rolang language in K.
Mm-hmm.
And once you have a complete definition, will it be possible to generate a compiler from K? A compiler that compiles to their method?
So,
Or LLVM or something like that?
unfortunately, well, okay. So in one sense, yes, and in the other, no. So part of this process sort of makes its own little compiler that's not very efficient and not very desirable. But it is useful in the senses that we just showed. Oh, sorry, if you want this clicker, you don't? Okay.
Just use the normal thing. Oh, that's why.
That's why, yep. Okay, in the other sense, as of yet, no, there's no way to just sort of take your K code and make this nice compiler, unfortunately. So right now, what kind of has to happen is that you have an implementation of K, and you need to show that it matches, this framework, that it's not a straightforward process. So there's lots of work to be done in this field.
But then you could use this to verify contracts. So you would run contracts and you would have all the possible solutions and then analyze this. So this is the intention?
Pretty much, yes. So if you are confident and willing to accept, any risk that comes from accidentally not made an implementation that totally matches the framework, then you can take a contract. You need to sort of abstract it a little bit and write a spec for it that works with the K framework. Then you can say, okay, here's some preconditions I want, here's some postconditions I want. I set up the preconditions, I run, I look at all possible solutions, and then for each of those, I prove that the postconditions are satisfied, and then you've just proven something about your contract.
So I assume this would be used from some tool that, so this is why you have that XML-like structure to parse it easily so it can collaborate with other tools.
Yes. Yep. Mm-hmm. Yep. That is the hope.
And what's how much of the current semantics of the language are implemented? So percentage, like
That's hard to say. I want to be optimistic and say 60 or something like that, but it's really hard to say. You never quite know. Every day I find nuances that are not ideal. So it's hard to say. Was there a question here? Wait, I didn't quite hear the question. Say that again.
Context-dependent grammars, are they supported?
Context-dependent grammars, are they supported?
Yes, like, for example, in some languages, other there can be in place of variable and in the place of function, you would pass it directly.
Yes, I believe so. I think the answer to that is yes. Uh-huh. Okay, any other questions? Great, okay. Go ahead, Mike.
Thank you.
This is work that I've done with Greg Meredith. Basic idea of a type system here is that propositions are types. So this is the thing we'll be working with. In the early 20th century, around 20s and 30s, various people were trying to formalize what logic meant and came up with different ways of expressing these formal logics. It was realized that implicational intuitionistic logic corresponded to something called the S and K combinators. So combinators were this thing that were, this idea that was introduced by Moses Schoenfinkel. It was later picked up by a guy named Haskell Curry, for whom the operation on functions currying is named, also the language Haskell. The point of them was that variable names are really hard to reason about, because you may have learned in high school, if you have f of x equals x squared, it's the same function as f of y equals y squared. The x and the y in that position don't matter to the meaning of the function. And it turns out to be fairly subtle to reason about these. So they invented combinator calculi to reason about binders essentially by eliminating them. So there's this process called abstraction elimination, and what ends up happening is all of your variable declarations get hidden inside these S's and K's, and S and K are essentially addresses for where this variable is used in the term. So you apply S to a variable, and then it distributes that over the two sides of an application. And if you apply K to a variable, it holds on to it. I'm sorry, if you apply Kx to a variable, then it will throw away the variable. It says it's not used here. So S says it might be used on the left-hand side of an application, or it might be used on the right-hand side. K says it's not used here. So given, but then you can then you can give types to these combinators. It says if I'm given something of this type and something of that type and something of this type, the resulting type is X. Similarly here, if I'm given an X and a Y, I throw away the Y and return X. So these two axiom schemata suffice for the logic, and when you combine it with the modus ponens rule, that if I know that from X I can derive Y, and I'm given X, then I get Y. This is how you write the S and K combinators in a fragment of ECMAScript 6, which corresponds to the lambda calculus. If I'm given A and B and C, then you can see here that it distributes a copy of C to A and a copy of C to B, and they're being applied to each other. Similarly here, if I get an A and a B, I throw away the B and return A. JavaScript doesn't have a static type system. It has some notion of dynamic typing. We have type of n here, where it'll return some primitive thing. You can also check instance of, but these runtime types are not very coherent. And so some programmers have taken to writing things called type guards, where you write a function that takes in a sample and says, if this sample is what I expect, then I just pass it straight through, otherwise I throw a type error. And so you can build up a full runtime type system that does pretty much everything you want in ECMAScript. But Microsoft and Facebook and Google have all independently invented static type systems for JavaScript, because you can't write maintainable code with only runtime type systems. What you get is people using your site, and all of a sudden it throws an error instead of knowing beforehand that your code had an error. This particular type guard here is an arrow type guard. It says if you give me two functions, these are two functions, but as we saw before, these functions in particular are type guards. If you give me two type guards and a function, then this will apply the first type guard to the input. So if you're not getting what you want, it'll throw an error immediately. Then it'll apply F to it, and if F didn't return the right kind of thing, it'll throw. So this puts a type guard in front of an F and behind an F. Makes sure that the full function is behaving the way you want. In the 50s, thinking about sets and reasoning formally about them, this set builder notation grew up as a way of trying to represent collections of things. How do we talk about the set of numbers? Well, this says this is the set of things n such that number is the type of n. Right? So anything that passes the type guard that we saw back here is used in this set builder notation, or is denoted in this set builder notation like this. So this says, I want those functions f such that for all values little a passing the type guard big A, f of little a is of type B. This is the arrow type guard that we just saw. So this is the type notation that was invented back in the 50s to deal with denoting sets by predicates. Here's how you would write it in Python. I want those values n for n in some particular list that I give you, where the type of n is an integer. So given a list of things, I want just the integers in that list. Philip Wadler wrote a paper called Comprehending Monads and said, hey, from any set builder-like notation, sort of somewhat simplified, but set builder-like notation, we can assign semantics from a monad. So this is the unit of the monad, return x. This is how we map functions over a collection, where the collection's given by the monad. And here's how we join two things together. So first, we'll read an x from this collection, and then depending on that x, we'll create another collection and read a y from it. And this is the monadic join. We've seen earlier today, just this talk, programming languages written in K. In 1963, I think, Bill Levere published his PhD thesis where he pointed out this vast analogy between work that had been done in what was called universal algebra and these new categories that had been talked about. And so in a Levere theory, what you have are sorts, and in K-framework we find these sorts as these syntactic things. So identifier and val and exp, we're saying what counts as one of these. And then we give function symbols which tell how to construct them. So how do you get a value? Well, you either have an identifier or you have the string lambda followed by an identifier, followed by a dot, followed by an exp, and so on. So we have these syntactic function symbols that build up terms, tell how to write a program. And then we have rules that say how terms evolve over the course of the computation. Now, Levere theories, as originally described, didn't have a notion of a rewrite rule. That came later. These are called enriched Levere theories. But if you have a graph-enriched Levere theory, then it's essentially the same as K-framework. So K-framework has grown out of Levere's work and this category theory work, but they're both doing the same thing. So here is a presentation of a Levere theory for the SK calculus that I mentioned earlier. I have one kind of thing, T, that's a mnemonic for term. I have two constructors, S and K. They go from the one element set, which means there's only one element. You can't choose anything there. So there's only one choice, into T. So essentially this says that S and K are terms. And then given any pair of terms, T squared here, I can apply one of them to the other and get a new term. And then these rewrite rules say if I apply S to X, Y, and Z, then it rewrites to XZ of YZ, just like we saw earlier. Similarly, if I apply K to X and Y, I'll get X. So K-framework, Levere theories, equal power in writing down what kind of language you want. But we can also write down our notion of collection as a Levere theory. It's a very simple kind of program that doesn't evolve. It's just defining some structure that we care about. So say we wanted a theory of finite sets. Well, we've got an empty set, and we can take the union of sets. And then they satisfy some equations that if I take the union of the empty set with something, it's just that thing itself, and so on. Associativity, commutativity of union. Structural types are expressions in a language that describe a collection. They are not collections themselves, but rather a syntactic thing that you want to interpret as a collection. So here at the bottom is an example of a TypeScript type where we have string as an entry in the record, number as an entry in the record, and so on down here. And so an instance of that type gives a specific string rather than the set of all strings. You can see that the syntax is pretty much identical, except that down here I'm allowed to use these special terms like string and number that describe collections of things, whereas the record itself can only describe one of them. So if I'm using the grammar of the term calculus, the programming language itself, and then adding in some stuff to describe collections, then I have a structural type. Here's another example of one where this 43 is not just a specific instance, but is now denoting the set containing the number 43. And over here, in TypeScript, you can use the bar to union two things together. So this is the two-element set consisting of Joe and Joseph. This is the one-element set 43, and this is the one-element set 1, 2, 3, and the one-element set sum av. So this is still denoting a set, and it works out to be the two-element set that looks like this, and the other one with Joseph replaced there. So there are these expressions that we can type that describe collections. So when I said that you add them together, this is the process of adding them. First, you identify two of the sorts. We've got a sort that describes what a program is and a sort that describes what a collection is, and we say, now they're the same thing. We union all the function symbols together, we union all the equations together. So here's an example. Monoids we're going to use for our notion of collection. That's just lists. Piano arithmetic, we have 0 and successor. There are no equations. So the theory of piano arithmetic, you've got 0 and the successor of 0 and the successor of the successor of 0 and so on. They're basically tally marks with an end of string symbol. So we think of these as 0, 1, 2, and 3. Every Levere theory corresponds to a finitary monad. So you might ask, well, what happens when I apply this monad to another set, like, say, the set containing X? Well, then I can also write down things, the successor of the successor of the successor of X. So we can take this free construction on a set containing some atomic numbers. We don't know what they are. They're just given as numbers and get expressions like this. We can also get non-standard models of arithmetic where you can toss in infinity as one of your elements and talk about the successors of that. So it's a very powerful way to think about numbers. Here's what we get when we add the two together. We have one sort, we identified them. We have 0 and successor, but we can also use I as one of the symbols in our language, which is the identity, and this times symbol. And then we have the associativity and unit laws for lists. So here's an example of an expression you can write in this new language where I'm using comma instead of times just to be more clear. This is the successor of the successor of the successor of a list. And in that list, we have similar terms. Well, there's a 0, there's a successor of some other list, and the successor of the empty list, and so on. Right? So this example is a structural type in this new type system.
Let's see. Right, that's just what we went over. Here is the other side of the predicates are types idea. This one is the theory of how you would get collections of terms. So before we were giving a language for expressing what a collection should be, and now this is the meaning of it. So on the left-hand side, what we just went over was the syntax, and now this is the semantics. So here we want lists of things in piano arithmetic. So here, I can't recurse once I've gone inside the list. I only have one list on the outside, and then I have numbers on the inside. So the interpretation of a formula maps from a structural type to a collection of terms, and we can build both sides out of those two monads that we already saw. When we take the sum of two theories as monads, it looks like this. So I've got terms here, collections here. When I apply it to some set X, the resulting sets are X itself, or terms with X's as atoms, or collections with X's as atoms, and so on, and we get all possible combinations of C and T. Now we need a distributive law. What we want to get is all the C's on the left and all the T's on the right, because at the end we want collections of terms. So here, this is taking something that is a term over collections, like we saw with the structural type, and returning a collection over terms, which is the meaning of that structural type. If we think of terms as products, right, when I'm applying S to K, we can think of that as being sort of like S times K, and collections as sums, that when we have X comma Y comma Z, that's sort of like X plus Y plus Z. Then the distributive law is named this because we're going from a product of sums to a sum of products. And here's an explicit example. Say we had recursion back and forth this way in the structural type. So this was a term over a collection. So we get down deep in there and there's a list, and inside that list is another list, and then inside that are just terms with X's as atoms. Well, what do we do to these? We can use, from TT, we can derive T using the join of the monad. From CC, we can get C using the join of its monad. Then we can use the distributive law. TC goes to CT, right there. And then we use the join on the T's again, and we end up with a collection of terms. So given a structural type, there's a very clear way to go from the type to what the type means. The distributive law doesn't always exist. If we're trying to use the SKI calculus for terms, there are two different ways around this square. So we're applying K to W and then XYZ. Now K, of course, throws away its second argument, so we should just have W here. But if we distribute first and then point-wise throw away the second arguments, we end up with a three-element list. So a one-element list is not the same as a three-element list. This is a mismatch between the idea of a linear type system, a linear logic, and SKI, which captures the ability to duplicate and delete things. You can't do that in linear logic. So if your type system, if your collection monad doesn't match your term calculus monad, you can't define this distributive law. So if we wanted to use SKI, we would have to use sets, right? Because the set containing one W is the same as the set containing three Ws. You can have as many copies as you want. They're all equivalent to each other. So this gives us a really powerful language. Now I can write things like this. This picks out all of the primes in any monoid. So if our monoid is the monoid of multiplication of integers, this will pick out the normal idea of primes. This says it is not the identity, so it's not 1, and it's not this expression. This expression says it's not the product of two numbers, neither of which is the identity. So a prime is something that's not 1, and it's something that can't be factored into 2 parts unless one of those parts is the identity. So like 5, right? It's not 1. The only ways to factor 5 are 1 times 5 and 5 times 1. So both of those factorizations involve 1, so it's prime. 6, on the other hand, we can give 2 times 3. Those are 2 parts, neither of which are 1, so it's not a prime. We also can get fun things called modal types, modalities. Not going to get into much depth on this right now, but this right here, this says the source of W is this K term, and the target of it is this V term. This is an expression with set builder notation describing what it means, so we can use collection monad to describe it. It says, this is something where I have a type A, a type B, and a term context. I said, I want all those terms such that there exists a U of type A and a V of type B, so when I put it in the context K, when I put T in the context K with U, then the resulting thing is of type V. So when my context is application, this says, I want something that when I apply T to something of type A, I get something of type B. Well, the things that when you apply to A's, you get B's, are functions from A to B. So this modal type here corresponds to the standard arrow type in Hindley-Milner logic. Using these modalities, we can then look at more interesting things, like in the pi calculus, this par here is a commutative operator. Application isn't commutative. F of x is not the same as x of f. It doesn't even parse in most cases. But par, if I'm running p and q at the same time, it's the same as running q and p at the same time. So this becomes an interesting sort of modality, something that when I par it with an A, the whole thing evolves to a B. So I want to describe those terms that when I run them at the same time as my contract, I get this other thing. Now that ends up being important for security, right? I want it so that it's not possible that there is an X on which it's sending the secret thing that I don't want to leak in parallel with anything else. So this is a very small type that if the compiler checks it, it means that thing is guaranteed not to leak because there is no context in which you can put it where it leaks. So this structural and behavioral type system derived from the term calculus itself and some notion of collection becomes a very powerful type system in which you can express liveness, security properties, all kinds of fun stuff. And since it uses the technology that's basically K-framework, we are hoping that Martin Lundfall and some of his associates will be able to implement this ladle idea for arbitrary languages. We're going to do it by hand probably for Mercury and perhaps Venus, because we don't want to have to wait for his work to complete in order to give a type system for Rolang. But the future idea is that you can run this over any programming language that you have operational semantics for, and K-framework has it for LLVM and JavaScript and EVM and a whole bunch of things, C, Java, and then derive a type system from it, and then go query, say, GitHub for any code that matches this particular behavioral type that I want to give you. And so you suddenly have a very powerful way of querying code bases. If you can express any other dynamical system, like, say, the biochemistry of a cell, if you can express those rewrites in K-framework, this reaction occurs and gives me that other chemical. Then you can query the chemistry of a cell for things that cure diseases, say. We're not claiming that these queries will be efficient or easy to implement, but at least now you have a language in which you could express them and try them on all of these big biochemical databases. So this idea of logic as a distributive law has been Greg's vision for 20-something years, and it's been a real pleasure working with him on bringing that to pass, and we're excited to apply it in a real-world situation on Rolang. Thank you very much. Yes, linear lambda calculus gives the BCI combinators when you apply abstraction elimination to it, and those work with lists. So in particular, if you have sets of lists of composable rewrites, you get quantiloid semantics for linear logic. So, depending on which collection calculus you use, it supports certain term calculi, and you get these fun logics out of them. Other questions? Yeah?
How do we type check that, say, 42 is not a prime? Like 42 as a bare integer?
Well, it's, as hard as factoring. The type system doesn't make this easier. It just makes it possible to write down the type of a prime.
So you're saying I can write down that type?
Right, so basically what it would do is a brute force attempt at factorization. It would say, is this an integer? And I would say, I'm sorry, is this the identity? No. So can it be split into two parts? Well, let's iterate over all possible successors, right? If you're doing it as piano arithmetic, well, can we split this up into chunks where they're all even? And it brute forces all of those different ways, and then finally finds one where, yes, I get 2 and 21 is one of them. And so then as soon as it finds a counterexample to the type, it would break out. Right, so the question is, how efficient can we make this? That is an excellent question. It's an open problem. That said, Luis Caires had the idea of a spatial behavioral type system. He didn't have this automatic way of deriving it, but he's published several papers on which kinds of types are efficient to type check. And so if you write programs, or if you write types that are efficient to type check, then you'll be able to type things very quickly. If you write more complicated types, well, it'll take longer to do. And now we have a market for distributed type checking, right? That you can charge for time doing type checking instead of doing compilation or SETI at home or something else. So.
And would the don't leak type be spatial?
No, don't leak is the name of a variable that I didn't want to leak, but that.
Could it be expressed as an efficient type?
Note that possibility on the left there. This says, I don't want it to be possible to evolve into that. And modalities are behavioral types. They're the ones that concern the edges in the graph of terms and rewrites, as opposed to merely the vertices. I'm sorry, what? Oh, Caires, C-A-I-R-E-S. Great, thank you very much.